Water. Typical H2O is neutral. Why? Because it's what we drink and from what we are made. It consists of two hydrogens and one single oxygen bonded in a molecule to form this compound. But what is the actual concentration in our daily life, whether it's acidic, basic, salty, or regular plain old water? To check this nature, we actually calculate its pH, pOH, or neutrality. So in today's video, I will talk about acids, bases, and salts. Acids. The word acid is derived from acidus, which means sour. Acids give hydrogen-positive ions in an aqueous solution. The acidity of a solution can be checked by calculating its pH. pH stands for negative log of hydrogen ion. The pH of an acid varies from 1 to 6, where 7 is equal to neutral water. The pH can be checked by using a pH paper or a pH meter. There are mainly two types of acids, which are strong and weak acids. Strong acid, an acid which fully dissociates and gives hydrogen ions in an aqueous solution. Examples are like sulfuric acid, hydrochloric acid, and nitric acid. Weak acids, an acid which partially dissociates and gives less hydrogen-positive ions in an aqueous solution. Examples are like acetic acid, citric acid, and carbonic acids. To demonstrate this, I got out some concentrated solution of hydrochloric acid. When I opened it up, I was greeted with pretty strong fumes. These fumes cannot be observed through the camera, but in person you can actually see the fumes coming out. Other acids like fumic nitric acid and sulfuric acids can corrode and damage everything around them, depending upon the concentration of the acid. If these acids ended up on your skin and eyes, they can damage your skin and eyes within seconds. Therefore, such acids are only meant to be industrial grade, commonly used in labs and for cleaning purposes. So with this in my fume hood, I opened it up and added 3 milliliters of concentrated hydrochloric acid into a grad cylinder, followed by 7 milliliters of water. In terms of safety, always add acids to water, not water to acids, as it can boil off exothermically, so we don't need to do this quite quick. We need to do it very slowly. Since it's very less, so it's not a big deal and it's just fine. Here is some universal litmus paper called a pH paper. I took off one of it and dipped it into the acid. It almost immediately changed color. Then comparing it with the graph, and it shows that the pH is close to 1 or 2, meaning that this solution is a strong acid. Makes sense since it's a dilute solution of hydrochloric acid. This is another acid, and I did the same thing where I took a pH paper and dipped it inside of this solution, and I compared it with the graph. And it shows that pH is close to 3 or 4, meaning that this is a weak acid. Makes sense since it's a concentrated solution of glacial acetic acid, which is a weak acid. Such acids like acetic acid is used in household vinegar. I also added a few samples into a few test tubes and added a few drops of liquid indicator, indicating that these are strong and weak acids according to the graph as they changed their color. Well, this was all about acids, and now let us talk about bases. Bases. The word basis is derived from basis, which means soap forming. Bases give hydroxide OH negative ions in an aqueous solution. The basic nature of a solution can be checked by calculating its pOH. pOH stands for negative log of hydroxide ion. The pOH of a base varies from 8 to 14, where 7 is equal to neutral water. The pOH can be checked by using a pH paper or a pH meter. There are also mainly two types of bases, which are strong and weak bases. Strong base, a base which fully dissociates and gives hydroxide negative ions in an aqueous solution. Examples are like sodium hydroxide, potassium hydroxide, and calcium hydroxide. Weak bases, a base which partially dissociates and gives less hydroxide ions in an aqueous medium. Examples are like ammonia, sodium carbonate and bicarbonate, and ammonium hydroxide. Such bases like sodium hydroxide is used in the preparation of soap. To demonstrate this, I got out some solid sodium hydroxide. Solid sodium hydroxide is also corrosive to the skin and eyes, and it can cause skin burns on hand if handled without gloves. So I replaced it with some concentrated solution of sodium hydroxide. So I took a pH paper and dipped it inside of the solution, which instantly turned purple-black. Comparing it, and the pH is close to 13 or 14, meaning that this is a strong base. Here is a dilute solution of a base called ammonia, and again I checked its pH. This shows that the pH is close to 11, which means that this is a weak base. I also added a few samples into a few test tubes and then added some liquid indicator indicating that these are weak and strong bases. Well, this was all about bases in general, and now let us talk about salts. Salts. It is the combination of a metal and a halogen. Such metals are reacted with halogens to make their respective metal halides. For example, sodium metal is reacted with chlorine gas to make edible and tasty sodium chloride, which is a common household table salt. A neutralization reaction is a reaction in which an acid is reacted with a base to make water and salt. To demonstrate this, I took a flask and added a dilute solution of hydrochloric acid with some indicator. And I turned on the stirring. This shows that the pH right now is acidic. So I slowly started to add dilute solution of sodium hydroxide. While stirring, after some time, it started to change the color. At a point, the reaction going on over here is that the acid, like hydrochloric acid, is reacting with sodium hydroxide to make sodium chloride and water in solution. When the color was close to yellow or green, I turned off the stirring and checked its pH. It was close to 7, meaning the neutralization reaction has completed. You can also see some salt precipitating out of the solution. Just for fun, I again turned on the stirring and added more base. The color slowly changed from green to blue, meaning that the base was starting to build up. At a point, it stopped, meaning that it won't change color until I add more acid to it. Well, this was all about salts in general, and now let us talk about titration. It is a common lab method which is used to figure out the concentration of a solution. To demonstrate this, I got out my beautiful burette and filled it up with about 25 milliliters of 1 m solution of sodium hydroxide. Then I took an Erlenmeyer flask and added about 15 milliliters of dilute hydrochloric acid along with about 5 ml of indicator solution. I placed the flask beneath the burette. After that, while shaking the flask, I started to drip the sodium hydroxide inside of the flask. Then, while slowly mixing the flask, I slowly opened the valve of burette and released the sodium hydroxide drop by drop. Now slowly while mixing, I monitored the color change. When it turned green, meaning the reaction is done, and this is the end point of the reaction. I repeated the experiment a few more times and it gave me this data. According to the initial and final reading, I placed the values in this equation, and after calculating, it showed me that the concentration of hydrochloric acid is around equal as the amount of base, which was required to neutralize equal amount of acid, which in terms makes sense since the ratio is 1:1. Well, this is it. I hope that you learned a lot, and if you like watching videos like these, consider subscribing to my channel and liking my videos, and I will hopefully see you in the next one. Thanks for watching.